So today we're going to do a game of life sequence. So something like this actually. So we're going to do an animation-based cellular automata. So we're going to implement some basic rules like neighborhood rules. And these are basically defined as rules of life. So let's look at cellular automata rules of life or game of life. Actually, this is from Conway's Game of Life. Let's look at that. So it's a cellular automata based on British mathematician John Horton Conway. And the way it works is actually it uses what we define as a neighborhood function. So imagine there's a grid. So like this, like a grid of cells. And you're looking for, let's say, a neighborhood. So for this cell in the middle, you're looking at these neighbors, okay? So every cell state can be active or dead, and depending on how many active or dead cells around the cell, you actually determine the fate of the cell. So that's defined by actually these rules. So any live cell with fewer than 2 live neighbors dies, as if by underpopulation. So we kind of look at surrounding cells and count how many of them are alive. And we determine the state of that cell in the next phase of the generation. And these are the other rules. So any live cell with 2 or 3 live neighbors lives on the next generation. So you have to have a minimum of 2 or 3 live neighbors. If you have less than 2 live neighbors, then you die because of underpopulation. Any live cell with more than 3 live neighbors dies, as if by overpopulation. Any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. So I think this is done. Every cell interacts with its 8 neighbors. So eight neighbor configuration is something like this. So you have a cell in the middle, and then these are your neighbors, right? So 1, 2, 3, 4, 5, 6, 7, and 8. So you have a total of 8 cells. So if you have less than 2 live neighbors, then the middle cell dies. Any live cell fewer than 2 neighbors dies, so it's underpopulation condition. 2 or 3 live neighbors advances to next generation. More than 3 live neighbors dies because of overpopulation, and any dead cell becomes alive if you have exactly 3 alive neighbors. So we're going to look at some of these conditions when we code this, okay? And this actually generates some sort of pattern behavior, and these are some of the established basically versions or configurations of cells, and these kind of create ripples or patterns. So you can see here, for instance, there's a pulsar condition, so you can make symmetrical generations as well. Blinker, toad, beacon. So I guess we could also start with kind of a condition for the middle of the animation, and then we can see how this kind of ripples or advances. And these are given names, but basically they follow those 4 rules, like these 4 rules, right? So if you start with a cell configuration state like this, then all of these cells actually interact with each other and calculate their neighbors, and that creates some sort of behavior. And that's what we call as the game of life. And this is actually pretty interesting because some people actually created these sorts of machines that can create some output. So this is kind of one of them. So you can make like mechanical simulations. Let me actually find one if there's any, like this one, buffer type reader. Yeah, so this is kind of like a cellular automata, but it's kind of animated, right? So it's kind of like a flying in this direction. But these are all individual cells, like small cells, and this is kind of the animation. And you can also have glider guns. Let's look at that. So somebody made this, for instance. So the cellular automata. Okay, so what you're seeing is basically animation of grid of cells. So we're going to start coding this. There's actually an example here called Game of Life. This is written by Daniel Schiffman as well. So I'm going to just reset it, but you can see this is basically a grid, and then these cells are alive. So it kind of stays in this configuration because it cannot update. Same as this one. So let's run it again. So you can see how they kind of move around and update the cell states, and that creates the kind of behavior. So there are a few things that we are going to code, but basically we're going to go one step at a time. Okay, we can also copy and manipulate it, but I want to show you some stuff that we should think about. So let's start with kind of a grid of 800 by 800. And I'm going to define, let's say, let cell size equals 10. So how many cells do we have vertically and horizontally? So we're going to have 80 by 80, right? So let's define that in a list. So I'm going to do let cells. So it's kind of an empty list. We could also probably do new array, but let's do it here. So I'm going to do for let I equals 0, I smaller than. What shall we do? Shall we do let num equals width divided by cell size? And then we do num I plus. All right, so this is going to be kind of the horizontal row, I would say. And then we could also do another for loop here. This is just to initiate our cells. So I want to first get the random configuration of cells so that we can visualize them along the grid, and then we're going to animate them. Okay. So for I, let j smaller than num. So this is kind of two-dimensional grid. So I want to first store these, or we could also do it like this. For instance, let's actually get the cells to work properly. So how do we visualize it? Let's do fill 0 and rect. So how do we do I and j, right? So we could do rect mode center. So I need to find the center of each rectangle. So we could do I times cell size. Let's make this smaller. So let's do CS for cell size. I times CS, J times CS, and CS, right? So that's the cell size. So let's see what kind of an error I created. Num is not defined. Let's make it here. Do let num, and we can declare num here and make it determined here. Okay, now all of them are black. The last cell is not generated, I guess. So we should do smaller or equal to. That's a black canvas, but I can also do it like this. So if random is smaller than 0.5, fill 0, else fill 255. So of course, this is not a cellular automata yet, but we are just kind of visualizing our grid. There's also probably some stroke because I see black black rows, but this kind of works well, right? So we need to be able to generate an array that stores these, and we need to update that list as well. So there are actually a bunch of ways we could do this. We could create a double array, like a nested array, and we can then access individual positions in the grid. For instance, I declared a variable here called cells. Let's actually write it here. So I'm going to make another copy of this double for loop. There's a different version of doing this in Daniel Shipman's code too, but we could do, for instance, this is, let's say, my horizontal row, and this is my vertical row. So rather than doing this, I can actually specify how many cells I want to be inserted for each row. So for instance, cells I equals new array, and I can declare how many I want, which is num. So I guess this works. And then we could do print cells. Let's see what that prints. Cannot set defining of setting 0. Cells, new array. I guess this is how it's done, no? So there's a new array columns. Yeah. New array rows. That actually works. So this is, num is defined here. Line 11, cells I. Okay, we first need to define this probably. So I need to do cells equals new array, you know, and then insert to each row a new array. Okay, so now you can see we have a list of lists, right? So there it says we have 81 slots, and all of these have arrays of 80 items. So let's see. So this has 79, but the array is actually 81. Let's see. I need a grid of 80 by 80. I got one more actually. Oh, it's because we need to stop here. So I need to just make it less. So now I say grid of 80 by 80 cells. Okay. And we can access each cell position using INJ. So technically speaking, I can do this. I can also do it like this. So for instance, I can check, I can store some value here. And then how shall we do it? Cells equals new array. And then we are nesting another array. And then I want to store some value. Let's say that value could be true or false, or 0 or 1, right? So that will determine the state of the cell. And I'm going to just visualize it under draw. So I want to first initiate a random configuration of cells and then just draw those cells rather than just like making them randomized. So new array num, and shall we do actually, we can actually Google this even, like how to initiate a random array of cells. This determines a new cell dimension. How can I do it? I can also do it this way. Like there's a short and a long way. I'll just show you the long way. For instance, if this is a double for loop, like this, okay, I can declare a new array, a new cell here. So cells I is going to be a new array. And then inside of this new for loop, I can just iterate through these cells. For instance, I can just do this. And for I, and I can make this J equals and I can do random less than 0.5. So what that will do is it will run this condition. So if this condition is met, it's going to store true or false under each of these cells. Okay. So when I run it, now I have a list of list of cells, and each of them either store a true or false condition, right? Because for some of them, this random called a condition that is true. For some of them, it called a condition that is false. And I'm storing it in the exact position of the cell at I and J configuration. And this actually reflects the configuration of the canvas. So now what I can do is this, rather than generating like a random call here, I can look for the state of the cell. So for instance, if cells I and J, so I can do it like this. And I need to also do it like this fashion, I think. And if the cell state is true, then it's going to be black, else it's going to be white. Now we're going to look at a static image. Okay, one thing I'm missing is you can see that the grid is kind of transposed a bit. It's because this rectangle is using center for rect mode. We can probably do it at corner. So let me actually find it on the reference of rect mode. Rect mode. So I want to do it corner. So let's do it corner. If I do it corner, then my grid fits perfectly to my canvas, right? So this is, every time I run it, I'll get a different random configuration of cells, basically. We can also start with the existing condition of cells. And let's try when we do 20. That also works. It's also drawing strokes around the cells. We can make, for instance, no stroke. So this is the no stroke value of cells. It's basically a two-dimensional grid of random cells. Now, the reason why we are doing it this way is because once we know the state of any cell at any position, we can then technically look at its neighboring cells, right? So remember that we have a grid of cells, and we have a cell in the middle. So I think this was called Moore neighborhood. So we are looking at these surrounding cells. So if this is I and J for any type of position, then we have to find the corresponding adjacency values here. For instance, this will be I minus 1 J. This will be, this top corner will be I plus 1, comma, J plus 1, right? Because I'm advancing both I and J. So, oh, this is J minus 1, sorry, J minus 1. This will be I plus 1, J plus 1. Because imagine this cell is at 2020, then the next cell is 2021, and this bottom right corner will be 2121, right? So that's basically, we are playing around with the indices to find the neighboring cells which are stored in the grid. So I can do it this way. I can have a function of checking the neighboring states, calculate the amount of alive cells, and depending on the current state of the cell, determine its fate, determine the next generation. So we can call a few functions here. For instance, I can do a function called next gen, right? And what I want to do is basically go through all the cells, and for each cell, look at its neighbors and look at its neighbor count, and basically get some value of active cells, alive cells, and use that alive cells value to actually determine these 4 rules of reproduction. So I'm imagining if the cell is alive, then we're going to look for overpopulation. So if the cell is alive, we're going to look for these the first three rules because it says any live cell, right? If the cell is alive, then we're going to look for underpopulation, overpopulation. And basically, if it has 2 or 3 live neighbors, it's going to continue to the next generation. But if it's dead, then we can only turn it to be alive if it only has 3 live neighbors, right? So we have to write these rules basically. So we can do them here. Next generation, what it's going to do is it's going to go through my cell list, look for the neighbor of alive cells for that cell. And then if the cell is alive, it's going to apply those 3 rules. If it's dead, it's going to apply a different set of rules. So let's actually do that. So I'm going to do another double for loop here. So this is how we access our list. And I can also do something else here. Basically, before I do this, I can do new cells, like create a new array equals cells. Can we do it this way? Like, would it copy the row? Let me look at how it's done here. Neighbors port, generate. Initialize, draw. There's a temporary port. And next is it will probably work. The board and the next. And next is defined as a new array. And we also have to apparently generate it. So it has to be something totally separate. So cells is the current state of the cells, and we have to do like a new cells. Or cells 2 maybe. Like cells next could be as well. So this is another array where we store a list of cells. So I'm going to do like this, another copy, and this new cells is going to be a new array. Then I'm going to overwrite an empty array as well. Something like this. All right. And we are trying to determine this list that we initiated based on the current cell state. And after we determine the state of these new cells, we're going to override the old one. Okay. So next generation. How do we do the next generation? So I'm going to go through cells and I'm going to look for neighboring count and cell state. So let's actually calculate the neighboring count. So I'm going to do let alive equals get neighbors, and I'm going to pass in I and j. And we can declare this as a function, right? So for instance, function get neighbors x, we can call it x and y here or something else even. So it's a new function call that I'm writing. And inside of this, what I'm going to do is I'm going to look for the adjacent cells of I and j, calculate the total number of alive cells. So let count equals 0. And what I'm going to do is we're going to do another double for loop, but this time I'm going to start from I is going to be x minus 1, and I is going to be smaller than x plus 1, smaller or equal to. And j is going to be y minus 1, and j is going to be smaller or equal to y plus 1, right? Because I'm looking to left, looking to right, but I'm going to skip the current cell. So there's also something that we need to be aware here. Basically, when we are calculating next generation, for instance, if I is 0, then we might want to look at a value that wraps itself around the grid. Because imagine if you are a bordering cell, if you're on the left top here, then technically speaking, you only have these three neighbors, right? There's nothing here on the left top. So you might want to wrap this value to the other side of the array. So basically, when I point here, it kind of goes all the way down. And when I point left, it goes all the way to the right, because there are 8 rows of cells here, 8 rows of cells. So this is index 0, but on the left, it will have a reading of 79th cell. And same here, 79th cell here, 79th cell here. And this would also be 70. This will be 80th probably if there's any cell here. But we could also do it in a way that we calculate. We don't look at the cell states at the border, or we don't update them maybe, and we keep them as it is. So we can do it with checking for I equals 1, j equals 1, and up to num minus 1 as well. So this would actually prevent us from going outside of the border. So let's look at the alive count. So what are we going to do? If cells I and j, so if the current cell is alive, then we're going to increment count. But I want to also skip a version, which is if I equals x and j equals y. So I want to skip the current cell. Continue, right? I don't want to check the state of the current cell. I just want to look at its neighbors. So this will return the total number of alive cell count. And then I will return a count. So this will return the neighbors. So we can actually check, debug if this works. For instance, this will generate or visualize the random amount of cells. And then I can click on any position on the canvas, and then I can get the neighbor count of those cells, and we can check if this works. For instance, function mouse pressed, and I can do print get neighbors mouse x and mouse y, but I need to be able to convert these to my I and j values. So what I can do is I need to define, let's say I get a pixel that is 750, then I have to divide it to the CS value, right? And then determine what the cell index is. So I can do it this way. I want to do a division, and then I want to do a floor. So that will give me the integer value, I think. Let's try. So if I press here, it has 4 alive neighbors. Let's see, if I test here, test the cell, it doesn't have any alive neighbors, right? So do we, yeah, if the cell is alive, we are printing black. So if I press here, it should print 0. So it printed 0. So the neighboring count kind of works. Let's test this one. This only has 2 neighbors. That works. This one only has 1. That also works. Let me press here. That should print 8. That also works, right? So we are basically looking at the neighbor counts, and this function seems to be working properly. So all I have to do now is to use that inside calculating next generation. So basically, we can get the amount of alive neighbors that the get neighbors function returns to me for every cell. And then I need to check if implement the game of life rules. So if the current cell is alive, so it cells I, j, that means if the current cell is alive, right? And this will be if the current cell is dead. So this is cell is alive. So what do we do if the cell is alive? We look for these first 3 rules. Any live cell with fewer than 2 neighbors dies. So if it's alive and if alive is less than 2. That means with fewer than 2 live neighbors. So fewer than 2 live neighbors means smaller or equal to probably. So if my alive neighbor count is smaller or equal to 2, this is rule 1, then the next generation cell would be dead, right? So I'm going to do new cells ij equals false. So elif alive, next rule is any live cell with 2 or 3 neighbors lives. So any live cell with 2 or 3 neighbors lives. So if alive is equal to 2 or 3, that would work. But what I can also do is check for this rule. Any live cell with more than 3 live neighbors dies. So what I can do is this: elif alive is greater than 3. So this is rule 3 actually. The reason why I'm doing it this way is because if I check for rule 1 and rule 3, then technically I don't need to check for rule 2, right? Every other condition will be basically will work. So elif alive, why didn't this work? Missing semicolon. Well, that kind of is else if. Okay, we have to write else if. So this would be overpopulation. This is underpopulation. And this will just make sure that it lives on. So this will be just true, right? It will stay as alive. But if the cell is dead, then we only check for one rule. So if alive equals 3. So that will make sure, this is rule 4. So this is turns alive, right? Because it has exactly 3 alive neighbors. So new cell becomes true. And at the end of this double for loop, what I need to do is update my cell list. So we have to do cells equals new cells. So I store my temporary cells here, and then I update them here. And this would actually visualize it every frame. And I need a way to calculate this or call this function, and I need to call it at the end of each draw. Well, that was fast. So let's make it actually frame rate 4. Yeah, that kind of works. So I kind of omitted the bordering cells because I don't want to wrap the values around yet. But you can see it kind of updates it. So let's make the cells a bit more. So you can see it starts this way. So if you want to add the neighboring cells as well, what we could do is this. So if we want to check for the borders, let's see, I0 starts from I and goes up to num. Then when I calculate for these positions, I need to make sure that the values are wrapped. So when I do x minus 1, that might actually make I as -1, right? And that might become an issue. So because we don't have a cell position in that location, so we cannot use I minus 1. So what I need to do is add I plus num and then mod num. So what that does is 2 things. It basically makes sure that I is wrapped. So if I is -1, I'm adding 80 for 80 cells. So I become 79, and mod 80 makes it 79 again. So -1 means 79 cell on the other side of the row. And when I is a greater value, let's say 80, then I'm adding 80 and modding to 80, and mod basically gives me the leftover value, which will turn it into be 0. So 80 itself for 79 cell will become 0 on the other side. I'm going to explain it on the canvas again. So let's see, let's make it like this. So this will also update the borders basically. And we are left with some small cells. Let's actually try to do something symmetrical. Basically, we start with a condition, let's say a random condition in the middle. How do we do that? So imagine that I'm doing a random state here, but then let's say that the state is false for all the cells, and I'm checking for some value. So let's say if, for instance, I can do it like this. So if I equals, let's say, how many cells do we have? We have width divided by CS, we have 80 cells. So if I is 40, then we draw this value. So we will have a random row, column of cells in the middle. Else, we just leave them to be false. Oh, what happened? Oh, because new cells is basically this has to be false. Okay, that was kind of fast as well. So we need kind of a few more things in the middle so that this kind of updates. So let's do if I is smaller than, well, I want to make it symmetrical. So maybe I start with an initial configuration. What can we actually do to make this symmetrically animated? So this pulsar, how does the pulsar start actually? Well, it's kind of a bit complex to code this, but penta is also interesting. I mean, if I can code this configuration to those cell states, that means that will basically be used. Maybe we could also do, I mean, we could also make it randomized. So for instance, if I is less than, greater than 35 and I is less than 45, then we make it random. So I'm just trying to make a group of cells in the middle random, and then this two kind of radiate around. And we could also do the same for J. Yeah, it kind of like dies away too quick. Maybe we do 25, and this is 55. Yeah, so that doesn't kind of ripple around. Probably the other way is better. I mean, this could be just here. I can just comment this portion out. So it's kind of like random all around. And one interesting thing here is that we also know the neighboring count, right? So for instance, while I'm drawing a rectangle, I can also make this colored because I know how many live or dead neighbors an individual cell has. So technically speaking, rather than just looking at its state to be alive or dead, I can apply some sort of tone here. For instance, I can write something like this. So how do I want to colorize this thing? Maybe based on the density of the neighbors, right? So if it has 2 neighbors, I want it to do something specific. If it has like 5 or 6 neighbors, I want it to do something else. So if the cell is alive, then I can also get its neighbor count. So for instance, I can do let n equals get neighbors for I and j. So I want to look at its exact neighbor count and then use n to make a fill value here. And that could be basically something like this. So I can do lerp color, and I want to do 2 tones there. How shall we do it? Maybe we could also do, if let's say n, the maximum number n could be is 8, the minimum could be 0. So technically, I can map that to something between 0 and 1. which is n divided by 8, and then lerp between two colors. And those colors could be determined here. For instance, let C1 equals, let's C1 and C2. And I'm going to just assign these to be some color values. So C1 equals color red, and C2 equals color 255. So this will be white. And I'm going to do here something like this. So fill lerp color C1, C2, and n divided by 8. Let's see what we get. So now I'm getting kind of tones of red, right? Because if a cell has, let's say, less neighbors, it will be a darker tone of red. If it has more, it will be a lighter tone of red. So we could also frame rate this to be really slow so that we can see the animation. So you can see it's kind of updating. All right, I can also do the other way for the background, like when a cell is dead, because we can also get its neighbor count, right? So I can get a neighbor count regardless of the cell state. So I can move it here. And we can also do lerp color here. Lerp color and color between black and between green, maybe? I don't know. And we could do n over 8 again. So when it's a dead cell, we can interpolate between two colors. I don't know how it's going to look like. Oh, it's super black. But you also get some grayish tones. Oh, so we are just interpolating between black and white for the background. Yeah, so the figure in the background is also updating. I can also make it kind of RGB. This might be too dark, but let's see. Yeah, so I have green in the background, red for the alive cells, and then I'm visualizing how I want to assign a tone. Yeah, that's basically it. So let's make it a lot more denser. Let's make this 5 and see. So there's a lot more going on, but because I'm starting with a random position for these cells and they're interacting a lot, we could also change these Conway's game of life rules. So for instance, if you want to see more alive cells left over, then maybe you can tweak these. So you can do, if alive is over than 4, maybe we make it false. And if alive is, let's say 3, I'm going to leave it as is. Maybe under population, we can reduce it to 3 as well. So let's see how this would change its effect. Maybe it's taking a bit longer to die, but most of them are dying. So maybe not 3. Oh, this is probably like canceling out a lot of cells. So let's actually make it less than 2 only and greater than 4. I'm trying to find a condition where we are left with a pattern, and this seems like it. So there's some sort of pattern emerging this way. You can see channels forming. Yeah, it's pretty interesting. Like some cells are still updating because they're not meeting this condition. But otherwise it's kind of, we are left with kind of a stable pattern. And now it might be interesting to actually run this almost like a patch. So for instance, I can make this part of the code active. And let's see what happens now. But it's probably going to like dissipate. Yeah, it's going to keep growing around. So it's establishing some pattern, and it's also moving around. We can actually make this a bit faster. Let's make this frame rate 5. So 5 frames per second. It's kind of moving around and growing into new cells. This is pretty cool because it's kind of leaving this part, like it's still updating some inner cells because there's some sort of flickering behavior due to these conditions. So I'm kind of changing the parameters for the over and under population. And you can also see how the simulation is wrapping itself around. The wrapping happens because I updated this neighboring condition with the mods. So basically for a cell that is here, I'm looking for like, I don't have any cell at the bottom of it. So what it does is it looks on the other side and it looks for the cell's state. So that's how I wrote this part of the code. So basically I'm wrapping the simulation around. So yeah, I'm going to stop here and see if you have any questions.
No.
No?
No.
Okay. So what we did was basically a Cellular Automata, and this is kind of a two-dimensional simulation. But what we are doing here now, we are updating each cell state based on its neighboring cells, right? So a cell, due to its gridded condition, has 8 neighboring cells, and we are looking at the current state of the cell, if it's alive or dead, and we are looking at its total number of alive cells, and that defines the Cellular Automata game of life rules. The default rule says that the underpopulation condition is less than 2, overpopulation is greater than 3. But I kind of tweak them to get some sort of pattern behavior. And we are updating this kind of list of arrays. So I have a state of cells that I stored in a double array. And then I'm trying to calculate the next generation of cells. And I'm basically, after I calculate the next generation, I'm overriding the cells with the new generation. And I do this for every update, every simulation, every state. And I get some sort of nice pattern behavior. I'm actually going to change it to be another color. Let's make it, do you have any color recommendations? Maybe not green, but yellow. Let's do this. Yeah. Red is okay, I guess. It's also updating pretty nicely. Let's make the frame rate a bit faster. So now it's updating faster, going faster. And I'm starting at this patch, right? The I and J patch is somewhere located here.